Okay, welcome to Data Focused Python Week 2. In Week 1, we took a look at the list collection type and talked about creating and accessing and getting slices from lists. This week, we're going to look at more collection types. We're also going to talk about type conversion among the different types and also web scraping. That is how you can go about going out to a website and pulling down data from the website and getting that into your Python program. All right, so we've taken a look at lists. This week we're going to look at tuples and sets as well. It turns out, by the way, that a stir can be thought of as a collection in the sense that you can ask whether a particular substring is contained within a string. So a tuple is a little bit like a list, except we enclose a tuple in parentheses rather than square brackets. We can index the items in the tuple from 0 to n-1, just like we can in a list, or in reverse, from -1 for the last item in a tuple back to -n, where n is the number of items in the tuple, which would be equivalent to the sub-0 item within the tuple. So I'm going to define a tuple n containing a, the string a, or the string a, as the first string in my tuple of strings, golden as the second string, eagle, and then soars. Okay, so if I ask what the type of n is, I see n is a tuple, and if I just type n at my shell prompt, the shell displays back to me the contents of that tuple. N sub 2 here is eagle, n sub -4 is etc. Now, unlike a list, a tuple is immutable. You're not allowed to change the items contained within a tuple. So if I say n sub 1 gets bald, all right, I'm trying to change golden to bald here, I get yelled at. I get told that tuple does not support assignment. And this is really the basic distinction that people make in a Python program between lists and tuples. Lists are modifiable and are thought of as containing dynamically changing data. Tuples are not modifiable and are thought of as containing input data that you got from some source and that you don't want to accidentally change. Now, although I have said that a tuple is immutable, that doesn't mean that the variable can't be changed to refer to something else. N currently refers to the tuple containing a golden eagle soars, but I can modify the variable n to refer to a different tuple, and of course that tuple can be constructed using parts of the original tuple that n referred to. So here I'm saying I want n to refer to a tuple built from the original n sub 0, which is a, and then bald, and then n sub 2 is eagles, n sub eagle, n sub 3 is soars. And so now n is referring to this new tuple of bald eagle soars. The tuple that n used to refer to, a golden eagle soars, I have lost my reference to, and so the memory for that can be reclaimed for use by some other object later on. It turns out that you can take the contents of a tuple and assign the items in the tuple to separate variables. This is making use of something called sequence unpacking, and it will work for general sequences, not just for tuples. All right, so n contains a bald eagle soars, and if I say A, B, C, D separated by commas gets n, The tuple on the right is going to be unpacked, and its individual items, A, bald, eagle, source, are going to be assigned into those variables. Or I should say those variables will be assigned to refer to those values. So A now refers to B to bald, C to eagle, D to source. Going the other direction, it turns out that you can also create a tuple without bothering to use parentheses. Here I'm saying T gets 1, 4, I, 4.6. This is the same as if I had stored those values inside of parentheses. And what I'm doing here is what's called tuple packing. T now is a tuple, and it contains the values 1, 4, high, and 4.6. Here's another distinction that people make in Python programs between lists and tuples. Although the language does not enforce this, generally we think of a list as containing items that have the same data type, and tuples are thought of as containing values that might have different data types. All right, so here I have a tuple of 4 items. 2 of those items are ints, 1 is a string, and 1 is a float. But again, I want to be clear that the language does not enforce this rule. A list can certainly contain items whose types are not the same, and a tuple obviously can contain items whose types are the same. Now, by combining tuple packing on the right-hand side of an assignment operator with sequence unpacking on the left-hand side, we can accomplish what's called multiple assignment. For example, if I say A, B gets 0, 1, the value 0 becomes the value that A refers to. The value 1 becomes the value that B refers to. And in the example on slide 6, I'm simply using 4 variables instead of just 2. A, B, C, D gets string high, float 12.6, Boolean true, and int 9. Okay, so A, B, C, D refer to those things. A common so-called idiom making use of multiple assignment allows you to swap the values of 2 variables very easily. Here, A refers to high, B refers to 12.6. If I say A, B gets B, A, what happens here is that the values of B and A on the right-hand side are fetched first, and then the variables on the left-hand side are made to refer to those values. So A is going to be made to refer to the original value of B, which is 12.6. B is going to be made to refer to the original value of A, which is high, and I have therefore accomplished swapping the values of A and B. The same idea is shown on slide 6 with a couple of int values rather than a float and a stir, but the idea is the same. An empty tuple is simply a pair of empty parentheses. All right, so T here is a tuple. The length of T is 0. It is a correctly defined tuple with no items in it. Creating a tuple of 1 item is a little bit strange. If I say something like T gets parentheses 6, thinking that I'm creating for myself a tuple of 1 item, well, actually, T is just the integer value 6, because the parentheses here are the parentheses used for precedence modification, not for tuple creation. In other words, when I say T gets parentheses 6, it's the same as if I had said something like T gets parentheses 2 times 3. Whatever the value is computed within the parentheses becomes the value that T refers to. And so the type of T is just int in this case. In order to create a tuple of a single item, I have to use a sort of goofy notation consisting of the value that I want the tuple to contain and then a comma, followed by my closing parentheses. So T now is a tuple it has a length of 1, and it simply contains the single item value 6. Okay, so T sub 0 is 6. T sub minus 1 is the last item in the tuple, which of course is 6. So just remember that strange little quirk of needing to use the comma inside the parentheses if you want to define a one-item tuple. You can use slices with tuples. A tuple is a sequence like a list or a stir. And so this gives you another way of creating, in some sense, a modified tuple out of an existing tuple. N currently contains a bald eagle soars, but if I say N gets N sub everything up to everything up to but not including sub 1, appended with the tuple containing harpy, and because that's a one-item tuple, remember I have to use my comma, followed by all of the items in N from 2 up to the end. All right, so here's yet another way of, quote, modifying, unquote, my tuple. N now refers to the tuple containing a harpy eagle soars. And the original, well, the previous tuple that N referred to, a bald eagle soars, is now lost its reference, and so that can be reclaimed, that memory can be reclaimed for other use. All right, so that takes care of tuples. A third kind of collection, in addition to list and tuple, is something called a set. Now, a set of values can be defined enclosed in curly braces. Items in a set are stored in unsorted order, although you may be fooled at first into thinking that they are sorted. And just like a mathematical set, a set in Python does not have any duplicate values. So here I'm defining S to contain 1, 6, 5, 9, 2, 1, 6, 3. You'll notice that I have some duplicates here when I defined S. I have 6 occurring a couple of times. I have 1 occurring a couple of times. But when I hit the Enter key, that is taken as a fine definition. And the duplicates are simply eliminated from the set. So even though I had 2 1s and 2 6s when I defined S, S now contains just one unique copy of each value. S has a number of named methods, as the list type has a number of named methods. Now, order in a set is not meaningful, so whereas in a list we have a method for appending items to the end of a list, and another method for inserting an item at the beginning of the list or at some arbitrary place in the list, for a set, we just have the ability to add a particular value. Let me add a 7, and we'll see that 7 has been added to the list. Likewise, I can discard a value from the set. So now I have discarded the 7. There's another function, remove, which is like discard, except that remove will fail if the value you're trying to remove is not in the list. So if I say s.remove 5, pardon me, I said in the list, I meant in the set. So if I say s.remove 5, since 5 is in the set, this will be successful. But if I say s.remove, let's say 13, this gives me an error, specifically a key error, whereas discard just silently doesn't do anything. So if I say discard 13, Okay, no complaint. The pop method removes some item from the set and returns its value. The particular item that you get is undefined. You will get one item if there is an item to return. If the set is empty, then s.pop will fail. All right, so the 1 has been removed and returned from the set when I did s.pop. And if I say s.pop again, this will remove and return some arbitrary item. Now, I know what you're thinking. You're looking at this and you're saying, the first item from the set is being returned. Well, in these 2 examples, that is what happened, but remember that 2 examples is not quite the same as infinitely many examples. And I assure you, it is the case that the value you get back from pop is arbitrary. If I clear the set, then I still have a set, but the set is now empty. And if I ask for what the length of S is, I get told that it's a 0. Let me restore my original set. Let me just cheat, and I'll copy and paste this one up here. Okay, so now S has 5 items in it, and I can ask whether an item is in the set or not. So I can say 2 in S. That is true. 4 in S is false. I used to have a 5 in here, so let me add that back in. Okay, so our set now contains the 6 items, 1, 2, 3, 5, 6, and 9. Alrighty. Okay, and these values here on slides 12 and 13 effectively repeat several of the values that several of the examples that I just showed you here. In addition to these set versus item methods, where I'm adding an item to a set, or I'm discarding an item from a set, or I'm popping an item from a set, or clearing all the items in a set, there are also several set versus set operations that the set container provides. For example, let me create another set S2. All right, so I've got S. Now, all right, let me repair S so that it looks exactly like what we have on slide 15 here. So I'm going to say S dot discard the 1, S dot add the 7. So now S contains, whoops, I better discard the 2 as well. Maybe I can get away with popping it. Let's see if pop chooses the 2 here. It did. 3, 5, 6, 7, 9. All right, so now my S looks like the S at the top of slide 15. And if I define S2 to contain 3, 4, 8, 9, 10. All right, so now I have 2 different sets with some overlapping values and some different values between them. The set difference of S1 minus S2, if you will, which I can actually do symbolically in Python, provides for me all of the items that are in S1 that are not also in S2. So if I ask for S dot difference S2, well, let's see. So the items in S are 3, 5, 6, 7, 9. The items that are in S2 that are the same are 3 and 9. So when I subtract S2 from S, what I should get back are 5, 6, and 7. That is, the items that are in S that are not also in S2. Okay, so that's what I get back from S minus S2. Now, doing this the other way around, on the other hand, S2.difference S will give me all of the values in S2 that are not also in S. Okay, so 4 is in S2, 8 is in S2, 10 is in S2, but none of those three values are in S. So I get 4, 8, and 10. Aha, now notice, finally, at last, we have encountered an example where the items are not in order. Okay, so in general, in a set, all you can count on is that the items will be unique, but you cannot count on them being in order. The fact that everything was in order up to this moment was just a random implementation detail of this particular Python shell. Okay. Now, symmetric difference will give me all of the values that are in one set or the other set, but not both. So if I ask for S dot symmetric difference of S2, okay, 4 is in S2 but not S. 5 is in S but not S2. 6 is in S but not S2. And similarly, 7, 8, 10 are in one but not the other. So in other words, this symmetric difference, 4, 5, 6, 7, 8, 10, is actually the union of S minus S2 with S2 minus S. Intersection has the obvious meaning. S dot intersection S2 is the items that are common to both, which is just the 9 and the 3. I can also ask whether the two sets are disjoint, that is, have no items in common. I can ask whether one is a subset of the other or a superset of the other. And I can ask for the union. So let's see. So S dot union S2 is all of the items that are in one or the other or both. And it's definitely going to be the case that S dot is a subset of S dot union S2. I mean, that's sort of obvious. S has to be a subset of itself with the union of anything else. On the other hand, S2 is not a subset of S, so S2 dot is subset S is going to be false. Okay. In addition to using these named operations, I can use symbolic operations for several of them. For example, the ampersand symbol, S ampersand S2, is the same as intersection. So I'm going to get the values that are common to both. That's going to be the 9 and the 3 that we saw earlier. Whereas S vertical bar S2, the vertical bar here has the meaning or, and it does a union. S caret or circumflex or hat or whatever you want to call that thing, S2, gives me the symmetric difference. The caret symbol is the exclusive OR character when you're dealing with bit values. And so exclusive OR means that we're going to get things that are in one set or the other set, but not both sets. And so you can see that that's exactly the same as what I had up here with the named symmetric difference operation. And then finally, the minus sign is just the same as the set difference operation. Let me say S2 minus S, and we should get exactly what we got up here for S2 dot difference of S. And yes, that is what we get. Okay, so the examples here on slide 17 are very similar to examples that I've just shown you live here. One restriction on a set is that a set can only contain so-called hashable items. And hashable items, for our purposes, include all of the scalar data types. So an int, a float, a bool, a stir, or the special value none, these are all so-called hashable items. A tuple, it turns out, is also a hashable item if recursively all of its items are hashable. So what that means is that a tuple that only contains scalars is hashable. But if you have a tuple that contains a list, for example, that's not hashable. Okay, so why is a list not hashable? Let me create a list here. 1, 2, 3. All right, so list m is mutable. I can say m.append 13, let's say, and that has modified m. Now, if I create a tuple containing 1, 2.3, hello, m, here we have a little bit of a philosophical quandary, I guess, because T is a tuple. A tuple is immutable. So if I try to say T sub 3 gets 1234, I'm going to get yelled at. But that item, the sub 3 item, is a list. If I say T sub 3 dot append 123, has been appended to this list. Now, so here's where our philosophical quandary comes up, because it sure looks like I have modified this tuple. But from Python's point of view, I have not modified the tuple, because the ID of T sub 0 hasn't changed. It's the same as it was before. The ID of T sub 1 hasn't changed. It's the same object it was before. Likewise, the ID of T sub 3 is the same as it was before. So from Python's perspective, I used to have a list with this ID number in my tuple, and I still have a list with the same ID number in my tuple. So from Python's perspective, I have not actually changed the tuple, even though I've changed the contents of the mutable item within the tuple. And I know that is odd. But again, let's try this. If I say t.append howdy, of course this is going to fail. Tuple has no method called append. If I say t sub 3 dot append howdy, on the other hand, well, T sub 3 is this list. The list is mutable. I can append the string to the list. There's my string in my list, but if I look at the ID of T sub 3, the ID of T sub 3 has not changed. It was 18 blah 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 432, and it remains 18 blah 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 432. So, as strange as this seems, Python considers that I have not modified this tuple, even though I have modified one of the modifiable items within the tuple. I cannot create a set containing this tuple because it contains a mutable item that is a list. All right, so I can say S2 gets for 12.34, howdy, true, none, and I can create a tuple that does not contain any mutable items. 1, 2, 3, let's say. Hi, let's say as well, just for gags. All right, so here I am now going to successfully create S2 as a set containing an int, a float, a stir, a bool, none, and a tuple containing 1, 2, 3 high. Okay, so a tuple, all of whose items are hashable, is hashable. But a tuple containing a mutable item, like a list, is not going to be hashable. So a set cannot contain lists, a set cannot contain sets, and it cannot contain any other kind of mutable thing. But it can contain scalar types, and it can also contain hashable tuples. A fourth collection type in Python is something called a dict, or dictionary. A dictionary, unlike list, set, or tuple, contains items that consist of pairs of values. The first part of the item is the key, and the second part of the item is the value associated with that key. And when you define a tuple, you can use the colon to separate the key part from the value part. All right, so here I'm going to create a dictionary named N to E. N to E stands for name to email address. And I'm just going to hammer this thing in, and then we'll come back and talk about it. Okay, so because this whole thing is contained within curly braces, I can get away with defining it on multiple lines. I just noticed I gave it the wrong name. N to D is not what I had in mind. But that's all right. I'll just say N to E gets N to D. And now both N to D and N to E refer to the same dictionary object. This dictionary object, let me confirm that it is a dictionary. Type of N to E is dict. This dictionary object contains 3 items. The first item consists of the key John associated with the value jkostland@gmail.com. The second item is the key Al associated with Al's email address, al@alcorp.net. And then Bob, the key Bob, associated with Bob's email address, bob@bassociates.com. All right, so the length of this thing, N to E, is 3. And this dictionary happens to have strings as both keys and values. But that isn't required. That's just true in this example. What is required is that each key has to be a hashable thing. And the keys also have to be unique. That is, John, the string John, is hashable. It's also unique among the keys in this dictionary. I don't have multiple things with a key of John. There's no restriction whatsoever on the values associated with the keys. The values don't need to be hashable. The values don't need to be unique. The values can be lists, tuples, ints, floats, bools, none, whatever. To access a particular value in the dictionary associated with a particular key, you can use the square bracket notation with a key as its argument. So N to E sub John. If I could type, it would be good. N to E sub John uses the key John to look up the appropriate item in the dictionary, and what I get back from that is the value associated with the key John. In fact, I can use the square bracket as a way of creating items in the dictionary or modifying the values associated with certain keys. So here on slide 22, I'm saying N to E sub psi. Now, psi does not currently exist within the dictionary, but that's fine because I'm going to create an item with that key, and the value associated with that key is going to be psi at nou.edu. So now N to E has been modified, and psi has been added at the end. I did not mention so, but let me do it now, that the items contained within a dictionary are ordered in the value in which the keys were created. So when I created N to D, but that doesn't really matter. When I created this dictionary, the keys were John first, then Al, then Bob, and now I've created psi. And you'll notice that when I display N to E, John, Al, Bob, and psi remain in that order. That is an official change to the Python language. It was unofficial in Python 3.6. It is official in Python 3.7, is that the keys are guaranteed to be stored in the order in which the keys were created. Now, the key John, as we said, already does exist. I can either say N to E sub John to look up the current value associated with the key John, or I can do that on the left side of an assignment if I want to change the value associated with that key. So I'm replacing my Gmail address that I started with my Andrew email address. And actually, for me, of course, those both work. Now, these other people, Al, Bob, and Psi, are phony, so don't bother sending email to them. The dict collection provides a number of named methods, just as the list and set collections do. For example, I can get a value associated with a certain key. The distinction between get versus using subscripts is that I will get back a value even if the key doesn't exist. By default, I'll get back the value none if the key does not exist. So if I say N to E dot get John, that gives me back the current value associated with John. If I say N to E dot get Alice, what I get back is none. Now, recall, by the way, that the shell does not display none as a default thing. So I would need to say, let me create some variable, ret for return value, N to E dot get of Alice. And now if I print the value that was returned, I see that the value that was returned was none. If I did not want none to be the default value returned, I can specify a particular value. I can say N to E dot get Alice, and then as my default, I can say not found. All right, so instead of getting back none, I get back the string not found. Pop item. Here my notes are somewhat out of date. My notes say that it returns some key value pair. Actually, it returns the last inserted key value pair. So, or it returns the last inserted key. All right, so I'm going to get back from this psi, and psi will have been removed from the dictionary. So unlike a set, where when you pop a value from a set, you're not sure what you're going to get, here in a dictionary, you definitely will get the most recently added key. You can say that you want to pop a particular item by key rather than using pop item. And of course, you can clear, well, I say of course, I don't know if it's of course or not, but you can clear all of the items in the dictionary by using the clear method. Okay, so here are some examples that are similar to what I just showed live.